Okay, so I feel really pretty decent about that. Sorry, the audio. That was recorded in a different way back in the day with my like super cool headphones that I wore with a little mic right out here. And it wasn't as good. This is the best system I have so far. So hopefully the audio usually doesn't suck. So feel okay about that. More about thermochemistry. That's the plan. You absolutely need to know these things by the end of today. What a state function is. All right, we haven't. Ain't gonna. Okay, it's not hard, but you need to understand just what it is. And Tiffany gave me a good idea of it the other day when I thought, oh, hey, that's actually a really good example. And then enthalpy. Do you even know what I'm talking about? Then you don't. Nope, you'll remember when I say it. Okay, and then internal energy. These two are really important. This one's just like, oh, okay, whatever. It's E. We kind of already talked about E, but here we go. I don't make you do blue sheets this year, so you can ignore that. You should be reading. Okay, here we go. The first law of thermodynamics is not super hard. Don't write it down. It's that you can't create or destroy. Well, don't write every word. So you can write it down, just don't write every word. Energy, help me out here, cannot be created or destroyed. It's what it is. We've heard about that with matter. All right. All right, I'm going to give you guys, I'm going to tell you something right now. And for a few of you, it may annoy you. This is not one of Newton's 3 laws. Huh? Right? It's not. Okay. What that means is kids apply to be Sterling scholars, and then we do an interview. And I tell everyone every year this is coming. I told them last year and no one remembers. You're going to be asked, what are the 3 laws, Newton's 3 laws? And tons of people will say this one, or they'll say the law of conservation of matter, but those are not right. So they are, and I don't remember the exact order, but I believe so. An object at rest stays at rest unless acted upon by an outside force. Number 2 is an equation. That's what everyone thinks, and y'all wrong. That's number 3. Force equals mass times acceleration. And it is words. It will say the acceleration of an object is directly proportional to the force applied and inversely proportional to its mass. That's the real answer, but don't say that. F equals ma. That's your answer there. And then number 3, Sealy. All right, there you go. Every action has an equal and opposite. Oh no, oh no. You shoot a rocket and really it's just pushing the planet. And so the planet's like, screw you. So it pushes it out of the atmosphere. That's all it's doing. The Earth is literally pushing the rocket out of the atmosphere because it's annoyed. It's like, I'm huge. You can't shove me. I'll shove you. Okay. It's too late. Sorry. Was that question asked? It was. There's your warning. If you're going to apply next year for Sterling Scholar, Newton's 3 laws, 0 people this year got all 3. And that's common. It's actually common because a lot of people don't take physics. And even if you do as a senior, you haven't got all 3 of them yet. So you're like, wait, I know the law of conservation of matter or this, whatever. Okay, I'm wasting time, but you're welcome. Here we go. So the first law of thermodynamics, energy is not created or destroyed. And if I put energy in, it had to come from somewhere. If it is lost, it had to go somewhere. Okay, internal energy. I don't know, this is actually extremely complicated stuff, but don't worry about it. We're going to say it's the total of all the energies of that thing. And we have a name for a thing, and we call it a system. All right, the internal energy of a system is the sum of all kinetic and potential energies of all components of that system, and we call it delta E. Or sorry, we call it E. This is whatever. This is later. It's just E. Now, there's so many things in stuff moving around and doing things and having temperature and all that. But this is extremely complicated to just look like at this tape dispenser and say, I think that has 58 joules. Like, I don't know. But we can measure when we change things. Okay, so we're really going to talk about the change in energy, which boils down to a different word that we learned. Anyone remember what that was? Enthalpy. Okay, so you don't have to 100% understand all the parts that make up the internal energy of a system, as long as you're okay calculating the change in that energy, or also known as enthalpy. All right, next. Whatever, we kind of already did this. Whatever, we already did that. And we got, okay, we get this equation, which you don't have to write down or know. I stopped you in time. There is an equation, and it used to be really, really focused on the AP test, but it's not been removed, but the math behind it is not asked anymore. The concepts of understanding that energy can change, they're still there. But so delta E is when the energy of the system changes. And it can be calculated from E final minus E initial, or it can be calculated from Q plus W. Now, what in the world is that? Q stands for heat. W means work. So there's basically two ways that a system exchanges energy, and it is by taking in or releasing heat, or doing work, or having work done on it. Right? Now, in chemistry, when we talk about work, it's super fascinating stuff. It's basically saying, all right, if we had a reaction inside a cylinder with a piston, would it make the piston go up or down? Well, okay. If the system causes the piston to go up, it is done work. If it goes down, work's done to it. That's it's so boring. Now, it got your cars here today. That literal application of chemistry made your piston fire upside down. The gasoline did work on the system, all right? It was the system, I should say. So it did work on the surroundings, caused that to go up and down, connected to a whatever, crankshaft, connected to a thing that spins with wheels on it, and you got here. But ultimately, the only thing that really was happening was the exchange of energy and the work it was doing on the surroundings. I know you care, but there you go. Okay, so change in energy is equal to Q plus W. All right, delta E, Q, W, and their signs. This can be a little tricky. I recommend you reading the textbook and or taking a picture of this slide. Here we go. First one of me as a 46-year-old. Do I look fat? Well, I should look fat. For some reason, since Friday, I've gained 4.5 pounds.
I heard somewhere that the camera adds.
Then the projector light adds 15. I'm actually super ripped and buff. Okay.
The microphone.
Yes. Here we go. So for Q, positive means that the system gains energy, or sorry, heat. I should say heat. It's okay. It can be energy, really. A positive Q means it lost heat. So endo versus exo. For W, a positive means work done on the system. Negative means work done by the system. For delta E, a positive means a net gain of energy by the system. Negative means a net loss of energy on the system. Okay, you rarely have to do math with this stuff. Like you'll never have this on the AP test. but you will absolutely have the application of this. You could have a sentence that says a system it gains heat and has work done on it. Is that endo or exothermic? You're like, hey, both those things it just said were endo. So it would be an endothermic process. Okay, it could say it has work done on it and loses heat. Then you'd have to do math, and it's just like 50 plus negative 40 or something like that. And then you'd say, all right, let's say, so 50 plus negative 40 would be negative 10 or positive 10, right? So E would be positive, and that would mean that the overall change was endothermic. Okay, you need to know really what plus and minus of delta E means. That's the most important part of this slide. All right, so when we have this ball that was really hot, oh, sorry, go ahead.
Endo means cold and exo means hot, right?
Right.
So if you touch it.
Yeah, it's what you observe, even though we're defining what happened to the other thing. And I have a little saying to memorize. Some people, this just doesn't help them out because they're like, no. But if you'll memorize this stupid sentence, you can remember three things. If you can memorize that your X was hot, but super negative, then you'll have the three things tied together. Oh, wow, that took a step into the awkward. So your X was hot, but super negative, meaning exothermic, produces heat and has a negative sign. Now, if you had a hideous X, that's on you. That's not my fault. All right. But anyway, all right, so here we go. In this example, the system, which was the red hot ball, gave heat out, right? So we knew that was a negative Q. Heat was lost. It came out. It exited the ball. All right, work. I have it equal to 0 because I didn't put it anywhere, right? I could have made this. If I put this in a sealed container with a movable piston, when that heated up hot enough and it produced steam, that would have moved it, right? But did I? No. So the work turned out to be 0. So the delta E would have been negative. It was nickel, which is a metal. You just want to watch a ball get hot in water. Okay, I mean, I can do that. Let me, I'll do it at the start of class tomorrow. Okay, are we sort of all right with this? It's not supposed to be hard, but it can be a little tricky. I think I had a question on it. I'll come back, don't worry. Here we go. Okay, think about this one right here. When a system blank, delta E is always negative. Will you think about these options? And here's the same table, so you don't have to have it memorized, but here's your table. When the system does what, delta E is always negative. Think about that for a minute. All right, what do we think? Who thinks it's letter A? Raise your hands. How about B? How about C? Okay, it is C. All right, what's that? No, because you could have a temperature change when you compress the volume. So it doesn't, Got you. Oh, okay. It's like a balloon, like you'd squeeze a balloon down. Okay, so if you add heat, you're adding energy, so it will always make it increase. Okay, let's come back to a state function. Okay, the slides I skipped over were endo and exothermic, and I feel like you're okay with those, right? Okay, so here we go. A state function. Usually we have no way of knowing the internal energy of a system. Finding that value is simply too complex of a problem. Okay, you don't need to write this down. I mean, you're welcome to, but that's a waste of your time. All right, so we have an example here. We have 50 grams of water at room temperature. It could have gotten from room temperature by cooling or heating. You okay with that? Its temperature is a state function because it is independent on how you got there. It doesn't matter. It's at 25. We don't care if it came that way by heating it or cooling it. We care that it is at 25. Yeah, there's tons of things. pH would be a state function. How far did you get? A state function is independent on how we reached it. What's that? Yep. So okay, go ahead. Yeah, how far you go, your distance versus displacement. Has anyone learned that in physics yet? All right, so we have Brigham City and we have Logan. You okay with that? A state function would be my displacement from here to here. My non-state function would be the distance I traveled, because I could go through the canyon, I could go to Tremont and over, I could go all the way over there through the canyons, up to Bear Lake, through the canyon and back. Why would you do that? Because you have 4 hours to kill as a driver's ed teacher. All right. You could go to Idaho and come down. All of those are ways to reach that state, which is our displacement or our location. But a non-state function would be the distance you travel. Okay, the example, and it was a stretch, but there's always like pretty pictures on Instagrams on the top of mountains, right? That picture exists whether the person drove up there, hiked up there, or was dropped off up there. And you're like, oh wow, that must have been a killer hike. You don't know how they got there. Like there's these famous picture in southern Utah, which is that way. Sorry if you're offended. All right, of these three dudes on the Three Sisters. And you think, man, how did they climb up those? They didn't. They were dropped off in helicopters. But who cares? They're on them. Do we care how they got there? No. Well, sometimes, yes. But no, their location would be a state function. So any picture, it's independent on how you got it, like how you got to that location, but whatever. So distance and displacement is the easiest example of what is and what is not. Okay, now, yada, 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 whatever, we don't care. Oh, though there was another example. Look how skinny I was back then. I was 193 last time I was on this slide. Whew. 211.4 today. So feeling good about my body. But my weight, 211, it doesn't matter if I was 220, like it would emotionally matter. But scientifically, it doesn't matter if I was 220 and lost weight, or I was 193 and I gained some weight. This was my lowest I've been in the last 20 years. And I should be at 185. My body functions well at 185. I'm really good at consuming drinks though, so I stay mostly between 215 and 205. Not that you care. Moving on. Anyway, my current weight is independent on how I got there. Self-esteem is not. Okay. Now, therefore, internal energy is a state function. It depends only on the present state, not how it got there. Easy enough? Okay. Now, however, Q and W aren't, don't write this down. Don't write it down. But we can make a battery dead by just connecting the two ends with wires. And that just makes heat, right? All right. So that would just heat it up and the battery would go dead. That would be just Q. All the energy would be Q or heat. Or I can connect the battery to a fan and then it will produce some heat, but it also produces work by spinning the fan. So the way that the path that it changed, oh, I keep doing that. The path that it changed does matter, but its overall change from beginning to end would be a state function. I don't know if that helps or not. All right, enthalpy, my friends. We already got that, right? There's some math. Remember I said I'd skip that part? Like there's a derivation of how enthalpy comes up. Because enthalpy is really all that stuff. All right, and then it's this stuff. But it's done at constant pressure, which means in an open container, which means there's no work. So work canceled out and H just ends up being Q and poof, enthalpy is heat. Now there's a lot more to it, but are you okay just memorizing enthalpy and heat are the same? Okay, if you're offended, feel free to look it up online. All right. I feel like we've been here before. This is where we were last week, right? Feel good about that? Okay. Okay, here we go. A couple more questions just for practice here. So we have, let's see, I don't know, 1, 2, and 3. You take a minute. You decide of your group which one's going to answer 1, 2, and 3, and then let's do it. Ready, go. Okay, anyone willing to tell me what they think number 1 is and explain? Anybody? Go ahead.
B because the water would be losing the heat.
Okay, the answer is B. Tricky. What about E? That's definitely endothermic because endothermic means cold. Because your X was hot, not your N. I don't know. So let's talk about it. Condensation of water vapor. It was a gas and it became a what? Liquid. So it went from steam to liquid, right? So it had to have lost energy to do that. If it loses energy, we call it exothermic. The energy exited the system. The other way around, A, it requires energy to evaporate water, right? So that would mean it's endo. Okay, I didn't even read the other ones. 2, which of the following statement is the first law of thermodynamics? Oh, that's not hard. It looks tricky. Anyone want to answer that one? Okay, a lot of you did. It is D. Energy lost by the system must be gained by the surroundings. It never just disappears. Okay, a blank delta H corresponds to a process. So do negative and endothermic go together? Nope. The negative and exothermic go together. Yeah, your X was hot, but he was super negative. X negative, or she, or whatever. Okay, so B is the answer, correct? Positive would be endo. 0 delta H, well, that would be no change, so whatever. We okay with those 3? Okay, you've seen 5 of the like 10 multiple choice that will be on the test so far. So they are right there. We're testing Friday. It's compared to chapter 3 and 4, it's like almost nothing. You really can. Okay, I feel like, did we talk about the math at all on Friday? Products minus reactants because it's final minus initial. Good. Okay, that looks like something I drew. Delta final minus initial. All right, we had that. Oh, I think we were bearing our testimonies on enthalpy. Is this about where we were? Okay. Did you get these? They're very important. Enthalpy is extensive because it does depend on how much stuff there is. So like the amount of calories on that cart is dependent on how many Mountain Dews are on that cart, right? And I'm going to take all that and put it right here. And then I'm going to complain about being fat. There's something wrong with that, but oh well. More Mountain Dew, more sugar, more energy, right? Enthalpy is energy. It is dependent on stuff, like the amount of stuff, so it's extensive. All right, forward and reverse are opposites. And I'm going to tell you, I think I said something wrong. I said it was Columbus. You remember that? It's 1429. Don't do your math on the test and get 1429. Be like, no, he said it was Columbus. My bad. It's 1429. There's your answer right there. Okay, a test question. Just put that feather in your hair. That doesn't make sense. Pretty sure. 1,429 kilojoules, if you care. I'm giving you too much already. So if you're not going to ever study, just put 1429 on every answer. And yeah, and you'll get 5 out of 100. Good job. All right, that's better than 0. Okay, then we were talking about number 3, right? And delta H for reaction depends on the state of the products and the state of the reactants. This is important when we go to do the math, because to do the math, you're going to find values in a table. And those values would have something like, so be H2O liquid, and it's like 493, H2O solid, it's like 385, H2O gas, and it's like 580. And I made those numbers up, so don't at me at all. Like I just made them up, but they're different. The energy of ice, even though it's still water, is less than it's like H2O, is less than liquid water because the liquid water is warmer. Thus, the liquid water would have more energy than the frozen water. That was a super lot of words. I worry that I confused you more, but I get paid to do that. So, yep. I take things that don't seem complicated and then I make them very complicated. Okay, moving on. Oh, yes. We have a reaction, we have numbers, we have words. Let's do this. Okay, this is from the textbook. So this is a very basic, super simple one, okay? So it says, when solutions containing silver ions and chloride ions are mixed, the silver chloride precipitates. And then you have new information you've never had before in reaction, and it's right here. It gives you the reaction, and then delta H is negative 65.5 kilojoules. Tell your partners right now, that process is something thermic. Exo, because it's negative, which means if I put that in the solution, into water, the water would become warmer. Did I hear a cold? I thought I heard a cold in a male voice. Okay. Your X is what? Hot, but negative. That's why you kicked them to the curb. Okay, here we go. So this value is new to you, and it means the energy change for 1 mole of reactants. Okay, so this one's nice. It's just a 1, a 1, and a 1. So we're saying in this reaction, if I had a mole of this stuff, which it's assuming I have a mole. That's what it's saying right there, since there's nothing there. Then it would give me that much energy. Fair enough? Okay, calculate delta H for the formation of 0.2 mole of AgCl by this reaction. It's really, really easy. I do what? Just times it. Now, I'm Tom, so I will do it in a picket fence, but you don't have to. So you are given 0.2 moles, and you're given the ratio that for every 1 mole, you have negative 65.5 kilojoules. So it's the same, right? I didn't super complicate it by putting it in a picket fence. You take the number of moles and multiply it times the kilojoules per mole. So I don't know, 1/5 of that, like 13. What? 13.1. Or B.1. And yes, it should be negative. Don't forget it. Thank you. All right, that's not hard, is it? Thumbs up if you can do that. Given the equation, given moles, just multiply. Okay. Now, oh no, is he really going to do me like this? Yep. Calculate delta H for the formation of 2.5 grams of HgCl. Well, everything we've done should have prepared you for this moment. What's my given? In the words, my given is 2.5 grams. All right, when in doubt, picket fence it out. I have 2.5 grams of AgCl. I want delta H, which is kilojoules. So I need to get rid of grams. So what do? What goes down here? Grams. Where do I get that number? BB's looking. Where did it? Yeah, right there. It's Ag and Cl. Is that 143? I feel like I should really have this. Sounds like 143. 143. We'll just call it good. That's the mass per how many moles? Per 1 mole of AgCl. What must be down here? A mole of AgCl. Do I have a ratio of AgCl per mole? It's negative 65.5 kilojoules per every 1 mole. Math, 2.5 times that number divided by 143. Well, it's going to be close to 1, isn't it? What'd you get? 1.15? All right, negative 1.15. I already forgot. Okay. Who's okay with that? Okay, there's going to be a lot of times where we use the picket fence, and it's not just grams or moles. It can be the energy. It could be the heat produced or lost in the reaction. That was the same thing, or taken in, I'm sorry. Speaking of, is this going to make it warmer or colder? To make it warmer, right? Yep, the surroundings will become warmer. All right. Okay, this one looks scary. When 0.150 millimoles of AgCl dissolves in water, yeah, you just move it over. So this would be 0.00015, is that right? Moles times 65, sorry, negative 65.5. You can do that in a picket fence as well. So if I get millimoles, I just do it at the end. I just find my answer and divide by 1,000. Either one works fine. Okay, so in these enthalpy, in the reactions, when you're given enthalpy, you can put them into a picket fence, just like they're the grams or the moles or whatever, to solve for what you want. All right, here we go. How many joules of heat would be released if 50 grams of Ag react with excess Cl to form AgCl? So we just did one just like this. annoying that it's so far apart. Okay, tell your partner what should be in the top left. What should be in the top left? 50 grams. All right, do I have 143 on the bottom? No, I have 107, right? Or 108 if I round it correctly. Why is it not 143? It was 143 last time. Because it's talking about Ag this time, not just Hgcl. Does that change the joules? No, because in this, it was a 1, a 1, and a 1, right? So this is negative 65 per one of those, per one of those, and one of those. Now, if there was a 2, then I would put the 2 in to the picket fence and life would be okay. All right, so coming back, per every 1 mole Ag, what must come down here? 1 mole Ag and negative 65.5 kilojoules. We end up with a number 30 point what? Kilojoules. Thank you. Okay, I want to warn you about something. We could solve for grams if we were given energy. Let's do it actually. We got 3 minutes. So how many grams of Ag plus yada, 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 who cares, with 200 kilojoules? Okay, now I'm almost out of time, but we would take my given 200 kilojoules, and what must be down here? Kilojoules, right? It'd be negative 65.5 kilojoules per every what? 1 mole. And then down here, I'd have 1 mole and I'd have 108 grams. You with me? When you type this into your calculator is going to give you a negative value because that math is a negative value, correct? But what's it asking you for? Grams. Can we get negative grams from something? No, this is negative because it's exothermic, but it's an amount of energy that can produce grams. So I don't know, did anyone type this in? What'd you get?
Negative 329.7.
All right, if you're solving for grams, never give me a negative sign. Because it wasn't really negative energy. It was energy that was released, but it's not really like a negative number. I don't know how to explain it better than that. So when asked for grams, don't put a negative sign. And we're going to do that 3 or 4 times this whole year.
But the energy is leaving the system, right?
Right, but it's still energy. Yep. Okay. I sense that we're done from something. All right, take a picture of this and try and figure this out tonight, would you? Someone put that in the group me.